Welcome to Professional Customer 87, and today we're talking about the aerodynamics of flying lizards, in particular the Draco lizard. And to do that, we're going to be looking at the paper called Combined Effects of Body Posture and Three-Dimensional Wing Shape Enable Efficient Gliding in Flying Lizards. So we've done quite a few podcasts on different flying animals, but none from memory on flying lizards and on at least gliding lizards. And it's quite amazing how efficient they are. And they are transient, so their aerodynamics are transient as we get into. They have three distinct phases: the takeoff, the gliding stage, and then the landing stage. And really only the mid-phase part, the gliding part, is where we have a steady flow. The other two phases, we have transient flows, and we have done other podcasts on transient lift production, and that's very interesting. So we'll continue on with this idea in this podcast. So this is open access. You can find it in the link in the description. So let's get on with it. So first up, aerodynamic performance is typically expressed as a drag polar plot showing the coefficient of lift versus the coefficient of drag. So the CD is on the x-axis and the CY is on the y-axis. Or you can also just have the lift to drag ratio on the y-axis and then the angle of attack on the x-axis, either one. The drag polar is just the CD versus CL. Positions on this plot reveal lift to drag combinations of interest, such as those that produce the greatest glide distance, the maximum lift, or maximum total force, as well as the sensitivity of the airfoil performance to the variation in angles of attack. And so drag polars, they're not that common in research, at least. I mean, in the aerodynamics, in the aeronautical industry, it's very common, but not so much just in general research, even though they are very powerful in terms of what you can glean out of them. So, although the airfoils of gliding animals possess fewer degrees of freedom than the flapping wings of birds and bats, characterizing the performance and the control of the actuated, compliant, and low aspect ratio airfoils have proved surprisingly difficult. So just talk about the low aspect ratio airfoils just for a second, and just how these are different to other types of flying animals. So first of all, bats and birds and most insects, they flap their wings, and this creates a transient lift production. And this is often characterized just by a lot of different vortices coming off from different areas. We've covered this in other podcasts, but just briefly, these vortices then produce these regions of low pressure and or help keep the flow attached over the airfoil so you can produce more lift and even potentially increasing the camber and thickness of the wings. So they act like thicker wings and more cambered wings. So you get an increase in lift from that way as well. With lizards and other gliding animals, they often don't have these sort of features, but potentially they do. We'll discuss it a little bit later. And as for low aspect ratio airfoils, so how is this different to high aspect ratio airfoils, and why do we need to know about them? So the aspect ratio is it describes how long the wing is compared to how like wide it is. So if you think about the distance from the leading edge to the trailing edge, that's the chord. Then if you think about from the wing root to the wing tip, that's the span or half span. So the greater the wingspan is compared to the chord, the greater the aspect ratio is. Why is this important? Well, just as a general rule, the greater the aspect ratio, the more efficient the wing becomes because you have a lower induced drag. So if you think about gliders, they can get up to aspect ratio, they can get up to lift to drag coefficients of about lift to drag ratio, of about 20 or even higher potentially. Whereas if you look at airliners like 747 or whatever, or 777, they're more around 10 to 12. And that's because they have lower aspect ratio wings as well as bigger fuselage and etc. So low aspect ratio wings, though, they have other added benefits. So if you think about how the wing looks, because they are very stubby, they have very big wingtip vortices. And this results in greater drag, obviously greater induced drag. But what this also does is it reduces the effective angle of attack. So this is a concept that isn't often discussed, and when you look into research and that and just books, they don't really discuss it too much. But when you look at the geometry of an aircraft, of an airplane, let's say, and the geometry says that it's at 3-degree angle of attack. It's not actually at a 3-degree angle of attack in reality, because you have flow being redirected around the rest of the fuselage and the wingtip vortices, etc. That will change how the flow that's actually hitting the wings hits the wings. So you can actually have an effective angle of attack of maybe 2 degrees, 4 degrees, 5 degrees, whatever. So wingtip vortices, what they do is that they push the air down, and this means that the effective angle of attack, so the angle of attack that the wings actually see, is lower. So what this means is you can push the wing to a higher angle of attack, geometrically speaking, and still keep the flow attached because the flow is being pushed down. And that means the effective angle of attack is lower and that means you produce less lift at the same angle of attack as a higher aspect ratio wing, but it means you can go to high angles without stall. So that's what aspect ratio is. I just wanted to cover that because it's a pretty cool concept that you don't hear too often. So let's continue. So numerical simulations onto this. Let's continue on this gliding lizard topic. So numerical simulations and wind tunnel tests of static animal models have provided an estimation of a drag polar curve for gliding snakes, lizards, squirrels, and fish, but do not address the aerodynamic effects of a compliant airfoil or mid-air postural changes, so flexing of the actual animal. Kinematic studies of gliding squirrels and sugar gliders have shown that the expected significant correlation between angle attack and aerodynamic force coefficients, but methodological limitations force these studies to examine a brief segment of the glide, lacking information needed to examine control of force production or the effects of the airfoil compliance throughout the entire glide. So in other words, up until now, regular studies have been very limited in where they're looking. They're only looking at brief instances in the actual flight, whereas they want to, in this paper, they want to look at the entire gliding, the entire flight phase. Overall, despite prior work on a variety of gliding species, the combined effect of changes in body posture and airfoil properties on the animal's aerodynamic performance and flight control, and ultimately the animal's gliding ability remains unclear. Here, they address these challenges by performing detailed aerodynamic measurements in a population of wild-caught gliding lizards, so the Draco dussumieri, that's the Latin name. They execute complete voluntary glides in this environment where they have cameras set up. So they can video these lizards gliding from all different angles, then construct a 3D model to see how the body is flexing throughout the entire path and what the actual body looks like in terms of airfoil, camber, and thickness and orientation, etc. Furthermore, they recorded the masses and the in-flight airfoil surface areas of the individuals to calculate the instantaneous values of the lift and drag coefficients for the complete glide. So the lizard's drag polar curve will have the highest lift-to-drag ratio occurring at low angles of attack, followed by the airfoil transitioning to a soft stall with an increasing drag coefficient and nearly constant not nearly constant lift coefficient, higher angles of attack. Let's discuss this. Why does this happen? So we mentioned that it's a low aspect ratio wing, as I mentioned before, and that means that the stall you can push to a high angle of attack before getting stalled. What's more, it will typically be at a softer kind of transition because you have these vortices pushing down a little bit and helping delay stall. So that's why you get this soft stall. Also, they say at low angles of attack, you have the highest lift to drag ratio. Why is that? The reason is because pretty much with almost every airfoil out there, not the exotic ones like delta wings, but just regular airfoils, at low angles of attack is where you're going to get the best lift to drag ratio because that's where you're producing a good amount of lift, but not much drag. The reason why is because you're not really taxing the flow too much. The more you tax the flow, the less energetic it becomes, which means the more likely you'll get little parts of the airfoil stalling, so flow separating, and also potentially increasing the induced drag by increasing the lift. So you get a reduced drag at low angles of attack, but you still get pretty decent lift production. And if you look at curves for regular airfoils, the lift coefficient will be linear to begin with angle attack, whereas the drag coefficient will be more like parabolic. So that means that as you get higher on attack, the drag just skyrockets. So at the low angles of attack range, the drag stays fairly constant. So it might be 0.02, for example, for like a 0021 at 1 degree. The lift coefficient will be 0.1. So you get a very good lift drag ratio there. Whereas when you go higher, then you get worse results. So that's why this happens here. So since the primary Draco, so the lizard wing, is formed by the activation of the intercostal musculature to rotate the ribs and stretch open the patagial membrane laterally, it restricts wing movement outside the dorsal plane of the body. So let's talk about this. I actually know this biological nomenclature, and the reason why is because I broke another rib a year ago almost, and so I had to learn about the intercostal muscles because it was important for this injury. So I can actually explain it to you what's going on here. So this lizard, it uses its muscles in its ribs to flex open this membrane, which also is connected to its arms. And this allows the membrane to stay fairly rigid while still producing lift. That's actually potentially a good thing in terms of gliding. What that does is it reduces the instabilities. So if you change a surface a lot, it introduces instabilities. And if you can't control those instabilities, you'll then lose control and you'll plummet to the ground. The lizard, by being fairly rigid, means that it may not have a great operating envelope, but it is still rigid enough to be stable. And that's being stable in flight is far more important than producing a lot of lift. Because if you produce a lot of lift but you're unstable, that means you're going to crash. Whereas if you produce a little bit of lift but you're very stable, it means you can control even a a bad landing effectively because you can still be stable. So that's what this means here. So similar anatomical restrictions are seen in other gliding species, including mammalian gliders, gliding snakes, and invertebrate gliders. Therefore, we hypothesized that or they hypothesized, not me, them, that the aerodynamic forces in the Draco gliding lizards are primarily controlled by varying the body orientation, specifically the body pitch, and consequently the angle of attack to enable a high lift-to-drag ratio during the mid-glide to cover horizontal distances, and high lift-to-drag forces at landing to minimize elevation loss while also reducing kinetic energy before touching down. So let's talk about this. They're talking about different parts in the animal's flight or the animal's glide. You have the main gliding section. When you're just regularly gliding, you want to have the greatest lift-to-drag ratio possible that will get you the furthest distance. But when you come down for landing, you want to throw off as much speed as possible so that you can land comfortably, nicely. So by increasing the drag coefficient, you can do that, but you still want to have a fairly decent lift coefficient so you don't plummet, you don't just like fall straight to the ground. It's a nice gentle touchdown. That's what they're talking about here. So in figure 1, they have this flight path. And if you're listening to this on our podcast, you can watch it on our YouTube channel. Link in the description, and we'll take you to our YouTube channel and you can see the video here, or you can just download the paper and look at it there as well. So the aerodynamics of gliding animals are deceptively simple, they say. To move through air, animals modify their bodies to form an airfoil and use it to generate aerodynamic forces by trading their height above the surface, i.e. the potential energy, for kinetic energy. So in other words, you dive down, the potential energy turns into kinetic energy, which is in the form of speed, and you can then develop lift. The generated lift and drag forces counteract the pulling of the gravity due to aero descent, and changes in magnitude and direction as the animal gains or loses speed, and makes postural adjustments along with changes in the airfoil shape. Together, these dynamic changes in the animal's body posture and morphology, and consequently the aerodynamic force production, allows the animal to execute a variety of glide trajectories and achieve different tasks, including mating, foraging territorially, and predatory avoidance, while accommodating their habitat's spatial complexity. Now, the way I read that was that they're mating while gliding. I don't think that's what they meant, but anyway, whatever. And this is the flight path here. So to begin with, they have the takeoff. Then most of the flight path is gliding. And then they have the landing phase where they sort of like flare their bodies up to dramatically increase the angle of attack and throw off a lot of that speed by increasing the drag coefficient, but also producing a little bit of lift still. And they have their cameras dotted around these flight paths. So in figure 2, this is an illustration of different body postures. So they have the lizard itself, and they have the different aspects of the lizard's body. So first of all, they have the yaw, and the yaw is, if let's say you put your hand out in front of you, and then you wiggle it from left to right, that's yaw. They have the pitch, so you get your hand again in front of you, and you rotate it up and down. That's the pitch. Then you have the roll, so you get your hand in front of you again, and you roll it left to roll it clockwise or anti-clockwise. That's roll. So those are 3 different moments. Then you have the angle of attack, that's related to the pitch. You have the camber, which is how much let's say you have your hand again, let's say you bend it at the knuckles. Then that means your hand is now bent at sort of like an angle, and that's cambered because it's not flat. And this means that you produce lift at 0 degrees angle of attack. Now we have a new concept called dihedral, and I haven't spoken about this too much on the podcast before, but I want to talk about it here because it's pretty cool. That's the geometry of it. So dihedral relates to how much, first of all, how stable the wing platform is, but this is through the angle which the wings are pulled up. So if you think about a regular airplane and you get the wing from the wingtip, and then you pull it up so it rotates about the wing root, if that makes sense. What that does is it increases the angle between the ground and your wing, how it's pointing up. This is called dihedral. And if you push it down, it's called anhedral. Anhedral, A with an A. So dihedral is a very good thing for wings because it increases its stability. So why is that? The reason is because if you think about your wing, let's say you got your hand and you have it palm up. So now this is your platform, and you bend your hand at the knuckles. Your fingers will be one side of the wing, your palm will be the other side of the wing. So that's dihedral. Now, if you rotate your hand about the knuckles axis, the one wing will go higher, the other wing will go lower. The wing that goes higher, the lift that's producing off this wing is actually now not completely in the vertical direction. There's a part of it which is in the vertical and a part of it which is in the horizontal. That means technically you're not producing as much lift on this surface as the other surface because just of this geometry. Also, the angle attack that the wing is seeing with the flow is now reducing. So you're getting less lift actually being produced because of that factor as well. What this does is it means that the wing on the other side, which is flatter, is actually producing more lift and a greater moment about the axis of roll. And then that restores the wing platform back to a more symmetrical geometry. That's how dihedral works. So that's very stable. There's another way that dihedral works to make the wing more stable as well, and that's effectively called the pendulum effect. So you have the center of mass usually is below the wings themselves. So it's just effectively like a pendulum where the mass naturally wants to rock back into a stable position. The alternative is called anhedral. That's where you flex the wings down, and this has the exact opposite effect. Most aircraft do not have anhedral. There are a few. They're mainly transport aircraft. For example, the Antonovs, which are Russian planes, transport planes. They are typically have anhedral, but that's not due to stability reasons. That's due to getting the wings off the ground. So when you're loading stuff in and out of the cargo plane, you can get your like trucks and that around easier. You don't worry about bashing into the wings. So that's practical concerns there. So let's move on. I've talked about the planform areas. So from the results, a total of 24 glides from 7 males and 7 female lizards were used for kinematic and aerodynamic analyses. The glides were recorded in a field motion capture arena consisting of a single fixed takeoff and landing tree spaced 5.5 meters apart with no obstacles in between. The average glide duration was 1.69 seconds, plus or minus a standard deviation of 5 seconds, with the lizards reaching a maximum speed of 5 meters per second. So that's pretty fast. That's 18 kilometers per hour. That's like a good running pace, or like a fast jog, slow run. The average overall glide angle was minus 28.3 degrees. So effectively, the angle attack was, or not the angle attack, but the way that the lizard was coming down was quite negative. And this corresponded to a theoretical equilibrium glide with a lift-to-drag ratio of 2. That's a very low lift-to-drag ratio, by the way, in terms of aircraft, but pretty good in terms of animals. However, none of the glides reached equilibrium. All show continuous changes in acceleration and speed in the X, Y, and Z directions throughout the glide. So this is what I've talked about before, it's transient. The yaw and roll angles were highly variable and close to 0 degrees across all glides. The average yaw was minus 3.7 degrees, plus or minus 3.6 degrees of the standard deviation. So that means that it was quite variable, as I mentioned. The average roll was minus 0.4 plus or minus 4.5 degrees standard deviation. So in figure 3, they show the average glide mechanics, across all 14 individuals in the field motion capture arena. So they have the pitch, the angle of attack, the percent camber of the body when they flex, the lift coefficient, the drag coefficient, and the lift drag ratios. Let's talk about these. First of all, the variation in pitch and airfall properties during the glide. During takeoff, lizards exhibit a high degree of variation in body pitch. However, after entering the mid-glide phase, body pitch stereotypically increased at an average rate of 11.1 degrees, which closely matched the trajectory shallowing rate during mid-glide of 11 degrees. So in other words, when they first take off, their body, they're really flexing a lot until they reach a stable point of about 11 degrees. That's and then they sort of keep that for the mid glide. The landing maneuver saw the average body pitch rate increase to 25.9 degrees finally per minute. Finally, at the end of the landing phase, the body pitch reached an average value of 51.2 degrees, which is a lot, with the lizard rotating its head dorsally and extending the forelimbs forward for touchdown. During mid-glide, the instantaneous changes in the body orientation and glide angle combined to hold airfoil angles of attack constant at 25.3 degrees plus or minus 2.8 degree standard deviation. Also, at this time, the lizard's airfoil maintained a concave downwards profile with an average camber percentage of 8.97 and a dihedral angle of 7.9 degrees. So there are a lot of numbers. Let's talk about this. When they first take off, they are trying to get quite a bit of speed up. That's because the more speed you have, the more that you can produce. Then they go into the mid-glide phase, so they're just gliding around. And here, they have an angle of attack of apparently 25.3 degrees on average. That's still very high for an airfoil when you think about it. Most airfoils during glide are around 2 to 5 degrees. So 25.3 degrees is massive, and that's partly just due to produce so much lift. It means you can have a smaller planform area, a smaller wing effectively, and you can still get around, which we're sort of looking at the lizard in an isolated fashion here where it's just gliding. We have to remember that the lizard has a lot more functions in its life than just gliding around. So having a really big planform, even though that is good for gliding, may not be good for other things such as running around because that's just extra weight, or even you have to consume more food because it's bigger, like more cells to reproduce. So the wing could be bigger in theory, but then that would probably hamper in different ways in life. So having an angle attack of 25.3 degrees is just an optimal angle attack for this wing planform that evolution has produced. Now, with the average percentage of camber, 8.97%, that means that the wing is fairly cambered, which means that it's producing lift even at 0 degree angle attacks. And the dihedral angle is 7.9 degrees, which is quite aggressive. That means it's very stable. After entering the landing phase, sorry, I should mention the landing phase as well. So the landing phase is where they just have to throw off as much speed as possible so they can touch down nicely. So after entering this landing phase, the angle of attack rapidly increases to 19.2 degrees, reaching the pitching rate increases by 19.2 degrees per minute, and it reaches a maximum of 60 degrees just before touchdown. So it goes from 25.3 degree angle attack to 60 degrees just before touchdown. But it can still produce lift at this very high angle attack, and that's probably due to the wing-tip vortices being so strong, as I mentioned earlier, the aspect ratio of wings. The landing phase also saw lizards using a significantly higher average percentage camber of 11.97% compared with the mid-glide phase, but with a similar dihedral angle of 8.2 degrees. So the dihedral angle is not that surprising considering that it's just stability based, but the increase in the camber is because it wants to produce more lift. Does that make sense? A steady angle attack of 25.3 degrees with modulations in camber during the mid-glide phase resulted in the lizard using a lift coefficient of 1.43 and a drag coefficient of 0.51. So the lift coefficient is quite good, it's respectable. The drag coefficient is a little bit high in terms of our airplane standards, but for an animal just gliding around, that's pretty sweet. In the landing phase, the lift coefficient and drag coefficient both increased at similar rates of 0.48 and 0.52 per minute. So as I have to mention, we have to remember that this is a transient situation. So these values are changing with the increase in the body angle attack and also the flexing of the body to increase the camber. The average maximum lift coefficient was 2.55 and the average maximum drag coefficient was 1.69. Both maximum occurred near the end of the landing phase, just before the touchdown. The average maximum lift to drag ratio was 3.22 and peaked early during the mid-glide phase at 1.69 meters from the ground, of horizontal travel. So this makes sense. Most wings, as we mentioned, they produce the best lift to drag ratio at low angles of attack because you're not taxing the air too much. But that doesn't mean that it's producing the highest lift or the lowest drag either, or even the highest drag. It just means it's the highest lift to drag ratio. Usually you'll get the highest lift at very high angles of attack just before stall. But at this point, you're getting a very high drag production as well. And that's what's happening here as well. That makes sense. And the reason why they're producing the greatest lift to drag ratio early on in its flight is that it's trying to get up speed to begin with. And so it means you want to have a low drag coefficient, and it's also just gliding around, just stunted glide. It's not trying to touch down or anything like that. So let's move on. They say the effect of airfoil properties on the lift and drag coefficients and lift drag ratios. So they use the calculated average glide mechanics in 3 multivariate linear models to test the combined effects of the angle attack, camber, and the dihedral angle on the lift drag coefficients and the lift to drag ratios during the mid-flight phase. So in other words, they just have a model that they're putting in different variables to see how these different variables affect the flight. And this is shown in figure 4 as the aerodynamic performance of the Draco gliding lizards recorded in the field motion capture arena as the drag polar, the lift and drag coefficient ratios, and the lift to drag ratio. So in the mid-glide phase, the angle attack and camber were significantly and positively correlated to the lift and drag ratio coefficients, but were negatively correlated with the lift to drag ratio. So that makes sense. We were just mentioning earlier where at long attack, you're going to get the best lift coefficient and usually the lowest drag coefficient, but not necessarily. And the higher the camber, the greater the lift coefficient, and also the greater the drag coefficient, actually. But both of these aspects typically reduce the lift to drag ratio. They say dihedral angle was not a significant factor in any model and was not included in the final model estimation. So let's talk about this and whether that makes sense. In this particular phase, in this particular situation, that may make sense, but in reality, that's not typically the case. The greater the dihedral angle, typically the less lift that you produce. Now, it's not a strong correlation, but there is a little bit of a correlation there, and that's mainly because if you think about it, the more dihedral you have, the less the lift vector is actually in the vertical direction. So you're going to get less lift overall. And there's also then the effective angle attack that the wing sees, which I'm not going to get into. I'll probably do a podcast on dihedral angle at some point, but we don't need to worry about the effective angle attack. Just think that the flow that the wing is seeing is at a low angle attack than what you'd expect it to be based on geometry. So the aerodynamic performance of the compliant airfoil. Their findings support the hypothesis that the lizard's aerodynamic performance is similar to that of the low aspect ratio airfoils at comparable Reynolds numbers and consistent with previous measurements of lift and drag ratios derived from the average glide angle of Draco lizards. The lizard achieved its highest lift to drag ratio of 3.1 at an angle of attack of 25 degrees, followed by a steady increase in lift and drag coefficients up to 55 degrees. After that, it showed a soft stall characteristic with a rapid increase in the drag coefficient without a drastic reduction in the lift coefficient. So that's pretty sweet. Moreover, the Draco gliding lizards produced higher lift to drag ratios at lower angles of attack compared to their gliding counterparts, including gliding squirrels, sugar gliders, and gliding snakes. The primary aerodynamic force generating surface of the lizard is the open patagium, so that's the like that membrane, forming a Zimmermann shape, like airfoil, with an aspect ratio of 1.41. So the Zimmermann airfoil is an interesting one. It's I'm actually going to do a podcast on this in the next few weeks, but it's effectively like if you think of an ellipse, then you cut it in half, and then you get the leading edge is the longer part, the longer section, and you put that forwards. That's the Zimmermann airfoil. And they say Torres and Muller showed that a rigid flat plate Zimmermann airfoil of an aspect ratio of 1.5 at Reynolds numbers between about 10,000 and 100,000 achieved higher maximum lift coefficients at higher angles of attack compared to rectangular airfoils like those of the mammalian gliders. Why is that? Probably because of the wingtip vortices, which are pushing the flow down, but we'll also look into that in a few weeks' time. The maximum lift coefficient recorded here in the Draco lizards was 2.6 at about a 58-degree angle attack, compared to the maximum lift coefficient of 1 at 45-degree angle attack for physical models of gliding squirrels, and a maximum lift coefficient of 2 at 35 degrees for gliding snakes. So in other words, these lizards have a far greater maximum lift coefficient than gliding squirrels and gliding snakes. However, this does occur at a much higher angle attack as well, which is probably due to its planform shape. So in the lizard's mid-glide phase, they observed that a significant rise in the lift coefficient at low angle attack associated with percentage cambers varying between 8 degrees and 10 degrees and a dihedral angle of approximately 8 degrees. The camber was significantly and positively correlated with its lift and drag coefficients, which is expected, and Bardera and others showed higher velocities on the upper surface of cambered Zimmermann airfoils, resulted in a region of low pressure and a mechanism for enhanced lift production. This is pretty cool. The Zimmermann airfoil has another little mechanism for producing lift, which is not the same as regular thick or even thinner NACA airfoils. But we'll have to cover this in a few weeks' time. Lastly, lower aspect ratio airfoils have the added advantage of the wingtip vortices generating low pressure regions over a significant portion of the airfoil. These flow structures can contribute to the overall lift production and energize the flow on the upper surface to keep the flow attached with increased angle of attack, thereby delaying stall. So you not only have this downwash, but these vortices also lower low pressure cores, which help the flow stay attached. Moreover, the delay in flow separation at high angles of attack could be facilitated by the placement of the lizard's forelimbs at the leading edge of the membrane, potentially acting as a leading edge slot and or changing leading edge sweep angle, although both these mechanisms remain untested. So let's talk about all this. So first of all, the wingtip vortices, when you have a very low aspect ratio wing and a very high angle attack, it kind of reminds me a lot of either a leading edge extension or a delta wing, where you have these massive wingtip vortices that low pressure cores and helps the flow stay attached. That's just a thought that came to my head. As for the lizard forelimbs at the front of the membrane, these could act as effectively tripping the boundary layer, making it more turbulent and potentially keeping the flow attached longer. I don't know. They said that it's untested. Then they have leading edge slots. I'm not so sure about that, because to have leading edge slots, you need to have a hole between the leading edge and then the rest of the wing. I don't know if that's actually the case for these lizards. I didn't see anything in this paper, but potentially it could be. And or changing the leading edge sweep angle. So how does the leading edge sweep angle help? It changes the stability characteristics, but also in this case, it won't change the lift characteristics too much, because the airfoil section is already very thin. It could help with potentially increasing the strength of the wingtip vortex. But again, that needs to be tested with this case. I doubt it. But anyway, that's the end of this podcast. And if you liked it, make sure to like, subscribe. And remember, in a few weeks' time, we'll look at that Zimmermann airfoil. It's going to be a pretty interesting one. And if you want to get better at theory like we're doing now, or better at CFD, check out our courses. We do them in the link in the description. And also, if you want to get your experiments to be 2 to 4% more accurate, and also that means your CFD validation will be 2 to 4% more accurate as well, check out the Atmosphere Hawk instrument that we make. We've pioneered that in the description. And we'll see you next podcast. Peace out, amigos.